Hi guys, nice to see you back. Last week we started a project to control a load, whatever is a lamp, an alarm, both, by using a light-dependent resistor or a photoresistor. And we were just putting the hand over it, and we could put it on or off. But we only discussed the first stage, if you take a look again on the block diagram. And this was just the signal amplifier. And we talked about how to connect the light-dependent resistor to the operational amplifier. Because I don't like unfinished business, let's do the rest of the job, meaning we're going to discuss quickly the signal conditioner and then how to make the on-off switch. Let's start it. Right here, I prepared the diagram to save some time, and I'm going to disconnect the alarm because it's too noisy. Okay, so I prepared the diagram containing the details of the electronic schematic for all the three stages. So I won't discuss this stage anymore because we've done it last time. It's the signal amplifier. I'm going to discuss the signal conditioner and then the on-off switch, how to make it. The signal conditioner is made using a very common and famous circuit, a version of the 555, and is arranged in the shape of a monostable circuit, exactly like you can see on the block diagram. What does it mean, a monostable circuit? The meaning is the stage is going to receive a signal and is going to get at the output a determined amount of time just to make sure that the next stage is not going to depend on the duration I hold my hand here, but anytime I do it faster or slower, it won't matter. The duration of this pulse given to the last stage is going to always be the same. So, how can we do this? Just because we want them to be triggered at the same time, and if you take a look here at this red LED, which is the output of the signal amplifier, and the amber LED, which is at the output of the signal conditioner, they both go on at the same time. But they don't behave the same way. So to make sure we get it, I'm going to quickly disconnect the load. Let me just do it from here, from the relay. I'm going to leave the lamp on all the time. And I can even remove the transistor from here, which is controlling the digital loggers. Remember the digital loggers, the one you can use instead of a physical relay to control a load. So now we only have the light amplifier and we have the signal conditioner. So here, if you take a look at both, the red light, anytime I put my hand over it, it stays. But the amber light won't stay. It's gonna be lit only for a very short amount of time. How does it happen? It happens because when you build the circuit, the monostable made with the 555, there is a little formula to use in order to calculate the duration for how long the light stays on. I'm talking about the amber light. So it's 1.1 times the resistor times the capacitor. What resistor, what the capacitor? Exactly that resistor here, R10 in our diagram, which is related to both pins 7 and 6. And the capacitor is C2, this one here, which is 1 microfarad. The formula is 1.1 times the resistor times the capacitor. And if I replace with the values 125 kilo ohms, I convert it in mega ohms, 0.1 to 5. Why in mega ohms? Because I need the 10 to the 6th power to cancel the 10 to the negative 6, which is the micro for the 1 microfarad here. I only need to do this very simple calculation, no need for the pocket calculator at all. And I get something like 0.14 seconds, is 1/7 part of a second. This is the duration the amber light stays on. Just to make you understanding how is this going, I'm going to remove this little capacitor here, which is 1 microfarad. I'm going to put it aside, and I'm going to replace it by another one. I have it right here, which is this one, 10 microfarads. So instead of being 0.15, 0.14 seconds, it should be something like 1.5 seconds, so longer. You should be able to see it. So take a look for how long the amber stays on. So even if I hold my finger on the light dependent resistor, so the red light stays on because I covered the light, the amber went off already because after 1.4 seconds it goes off. And I do this again. And if I do this quickly, it's still holding only for 1.5 seconds. I do this again. But if I continue to do it longer than 1.5 seconds, it's going to be obviously re-triggered after that. So you get this 1.5 seconds again. So this is what I should do. 1.5 seconds. Or shortly, 1.5, 1.4 seconds. See? Shortly or longer, it won't matter. Or even if I give more pulses. Okay, so this is to prevent the last stage we're going to build a bit later, to receive more than one signal at a time, because we don't want the contacts of the relay to go on, off too many times, okay? Because otherwise they are going to wear out. So this is how this thing is working, okay? This was the stage about the 555 used as a monostable circuit. This is the monostable, meaning it has a stable state, which is the on state, and you can get it off of that state for a limited time, okay? What is the limited time? Is the duration we use the formula for, 1.1 times the resistor times the capacitor. Not any resistor or any capacitor, but only these ones here, the resistor 10 and the capacitor 2, the ones connected to the pin 6 and 7, these two ones. So far so good. We trigger that signal by bringing it from the output of the signal amplifier through an inverter through that capacitor, and it goes on the pin 2, which is the triggering input of the 555. And then we get the output 3 of the 555. We monitor here the amber LED, which is about 10 milliamps. And then the signal goes to the next stage. What is the next stage about? So the next stage is anytime it receives a signal from the 555, if it was off, the output goes on. If it was on, next time it receives a signal, it goes back off. And this little trick is because the package 4013 is a dual flip-flop. What is the dual flip-flop? It has 2 flip-flop circuits inside, but we only need to use one. And for that reason, the second flip-flop, I put the pins regarding the second flip-flop in red. The outputs, you do nothing to them, you don't touch them, pins 12 and 13. But for the sake of the signal integrity, you don't want these inputs remaining floating into the air to catch unwanted signals like the static from the air. A good practice is the inputs you don't use from CMOS circuits, link them to plus, to the positive voltage. This is why the D2, the S and R2, and the clock number 2, all of them are linked to the +5, okay? Because we all need the pins which are in blue. And how the signal goes on and off is because it doesn't matter what is the output, normal output Q1. The Q1 with the bar in the top is the opposite to it. So it's going to take the signal and bringing it to the data input. So next time, if it was on, it's going to be triggered off, and so on, okay? Now, I know that these things may not be extremely clear about the flip-flops and the names of the inputs. And because I had some feedbacks already, I'm telling you that starting next week, we're going to enter a bigger chapter, which is logic circuits, because we have to clarify these things, otherwise they're going to remain unclear forever. One thing I can clarify today, though, is the names of these letters here for each of the two flip-flops. And as you can see, I'm going to put this one anyway on Google Drive, don't worry about. The letter D used on a flip-flop is the data input. Letter S is the set input. R is the reset input. CK or CLK is the clock input or the timing input. The letter Q always refers to the something we call the normal output. And the Q with the same number in our situation was Q1. Now we have the Q1 bar. The bar in the top says this is the complementary output. What is the complementary output? It should always be opposite to the normal output. Okay? So this was the meaning of the letters. Another thing we should clarify about this, when you plug such a package on the breadboard, it's always a very specific position you have to plug them on a breadboard. And that position is based on the fact that this is a socket, for instance. It's based on the fact that here somewhere, if I align it to my left, this is called a notch. So I'm going to put it right here to make sure we get it. This here is called a notch. Okay? And the purpose of this notch is simply to identify where is the pin number 1. This package has 14 pins. The other two packages, the signal amplifier and the signal conditioner, they both have 8 pins only. But the way the pins are numbered is similar. So right below the notch, if you take a look from the top, on the bottom left, you have the pin 1. And then you count the pins going counterclockwise. So the pin 1 closest to the notch, 2, 3, 4, and you continue on the other side, 5, 6, 7, 8, or for the bigger package, which is the 4013, you count 1, 2, 3, 4, 5, 6, 7, and then you continue 8, 9, 10, 11, 12, 13, 14, okay? And this is why here again, even on the socket you place these packages on, you have the notch. And if I take a look on this little package, I can see not only the notch, which is over here, but some manufacturers also put a dot. It doesn't matter the color. In that situation, it's white, it can be black, it won't matter. And the dot is right above the pin number 1, because that's the purpose, to identify where the pin number 1 is, to start counting counterclockwise. I have another example here. On this package, maybe you can see better on this one, there is a notch, you can see, but also there is a black dot right over the pin number 1. So you know how to count the pins. And it goes the same way. I have a bigger package here. It doesn't matter how big the package is, the notch is here, and you have a little mark right here above the pin number 1. Don't consider this big dot, which is exactly symmetrical versus the two sides, because this is only from the press putting the two pieces of plastic together, the top and the bottom of it. Okay, you can see there is a little edge right here in the middle, is because they put the two pieces of plastic together to cover the semiconductor, which is somewhere inside. Okay, but you have to consider this dot, which is above the pin 1, or the notch, showing you that the pin 1 is on the bottom left of that notch. Okay, so now we know it. And I'm going to talk much more about these kind of things when we start talking about the logic circuits. So that's how we connect physically the package. So I put them in such a way that all the packages are aligned with the notch to my left. So it's easy to identify where is the pin number 1, 2, 3, and so on for each of them. Okay? Good. One other thing I should have said before going to the flip-flop is that anytime you use the 555, the 555 has a kind of, let's call it a little drawback. through the power lines, it can propagate some signals, some unwanted signals, and you want these signals to be reduced at minimum. And this is why it's a good practice that right here on the package, you are going to place two capacitors between the pins 8 and 1. Why? Because on that particular package, the pin 8 is the positive voltage and the pin 1 is the ground. So right across these two pins on the package, you're going to place two capacitors, an electrolytic one, anything 4.7 microfarad up to 10 microfarad is okay, and another one 0.1 microfarad, okay? And if we take a look together on the board, this black body here is the 4.7 microfarad, and the little blue body right in parallel across the pins 1 to 8, both of them are in parallel across 1 to 8, this is the 0.1 microfarad, okay? So it's a good practice to put both of them together, okay? Good. So now back to the flip-flop 4013. What happens is, anytime it receives a signal on the clock input, whatever is found on the data input, it goes to the output. So anytime I press a signal on the clock input, if the data 1 finds on the complementary output a 1 logic, then it's going to propagate it and this one goes 1. But when this one goes 1, the complementary output goes the opposite to the normal output, it goes 0. So next time I put a clock input, the data 1 is going to be 0 instead of being 1. But being 0 going at the output is going to put the light off. And then by putting it off, the complementary output is going to be 1. So next time I press the clock input, the 1 is going to go to the normal output and so on. So this is why the output actually is flipping like a switch on, off, on, off. This is how it's working, okay? So very quickly, just to have an idea about how it's working. Now, I disconnected the output for the load, so I just removed this transistor from here because I wanted to see how the signal conditioner was working, how the monostable circuit was working. Okay? Because I don't want the lamp to wait for 1.5 seconds before going on, I'm going to replace the original capacitor, the 1 microfarad, right here across it. So when it's going to be triggered, it's only staying on for the 7th part of a second because it's 0.14, 0.15 seconds, okay? So during all this time, you couldn't see the green light representing the transistor of the load for the flip-flop because I removed the transistor. If I just remove the relay control completely and I just replace my transistor, have to be careful because even the transistors, they also have polarity, okay? So take a look what happens. I put the lamp on the digital loggers in an outlet which is always on, so this is why the light won't change right now, but you can see now the load is only represented by the green light, and take a look what happens. The green light goes on. Next time I put my hand over the cell, it goes off. Now it goes on and it goes off. It goes on and it goes off. And if I connect now back, it's very sensitive, okay? If I connect back the light right here, you can hear the relay. Why the light doesn't go off? Because I have to remove it from here and connecting it back on the normally off. So now it's going on and off, on and off. And there's something more interesting. I'm going to also connect the alarm and I'm going to show you something now I can control both the loads, the light and the alarm, by just putting on and off the ceiling light. Just wait a second to see, okay? Pay attention. So the light is off, the ceiling light is off. I put the control off. I put the ceiling light on and off. You see this? So I'm able to control with the ceiling light if the adjustments are right, okay? So basically, you have now the components, you know what is involved inside. See you next week to start with logic gates and logic circuits. Thank you very much for watching. See you next time. Bye-bye.